Okay. Share my screen. So, hi everyone. Welcome to the Multimodal Weekly webinar series hosted by team at 12 Labs. Whether you're new or you've been joining this session for a while, we've been meeting every Friday over the past 1 year or so. So this is the session number 45. Some of the topics that we tend to cover on a weekly basis, news research in multimodal AI and foundation models, innovative application of multimodal in different verticals. Since we focus a bit more on video, we also have like developers and founders who are working on respective video projects that they tend to share. And finally, we oftentimes introduce tutorials and guides from internal team members on using your technology. In some of this recent session, we have, as you see here, a wide-ranging diverse speaker persona, right? From like researchers working at the intersection of vision language model, visual augmented generation system to video agent. We also have some of our partners with 12 Labs, companies from the developer community like MassDB to more on the application layer, like surgical AI, to come and present some of their work partnering with 12 Labs. For today's session, we have actually two researchers, grad student working in foundation models and multimodal models. So the first speaker is going to be Seungone Kim, currently wrapping up his master at KAIST in Seoul in South Korea, and he's also an incoming PhD student at Carnegie Mellon. His talk will be around the family model called Prometheus, which the type of model families that is specifically changed to specialize in evaluating other language model. And this, I know this paper has been getting a lot of attention lately. So yeah, excited to hear more from Seungone and this process of developing this work. On the second half of the webinar, we have Nikhil Singh, currently a PhD candidate at the MIT Media Lab. I know he coming from a background from music, if I'm correct, and then now he's transitioning into, basically application of AI into creative domain, including music. I got connected with him, at an event at MIT last month, and pretty interested about some of his publication in multimodal understanding and human AI interaction, right? So for today's session, he will go over a couple of his work building multimodal models for enhanced audio processing integration. With that, just some quick logistic note. For attendees, feel free to send your question in the Zoom chat, and I can surface them to the speaker as they go over their talk. And we also have more like an informal Q&A session, probably 5 minutes after each speaker finish their presentation. So yeah, with that, I'll stop sharing my screen, and I'll let I guess Seungone go ahead with your part.
All right. So could you see my screen?
Mm-hmm. Yep.
Awesome. So yeah, thank you for having me today. My name is Seungone. I'm currently a MS student at KAIST and incoming PhD student at Carnegie Mellon University. Today I'll be talking about Prometheus, a series of open source models specialized in evaluations. So there were 3 works involved in this series, and it was a collaboration between KAIST, Naver, LGAI, CMU, UW, MIT, AI2, and UIC. So here are the table of contents. I'll briefly be discussing about why actually evaluation itself is a very challenging task. And then I'll talk about how we trained and evaluated our Prometheus model series. And then I'll talk about the experimental results followed by the future directions. So without further ado, let's get started. So why would it be important to have a LM or just a foundation model in general to possess very good evaluation capabilities? I think there might be a lot of applications or research questions involving this, but I've prepared 3 examples that I think a lot of people might be interested in. So the first is LLM as a judge. So recently in classification tasks, it's very relatively intuitive how you could judge or mark the predictions made by AI models. you could just like use accuracy to compare with the ground truth like label. But for generation tasks, actually, this is a much more challenging problem because even if you have a ground truth, it's very like hard to know if the predicted output is a good output or not. So previously, a lot of papers just measured the like semantic or lexical similarity between the reference answer and the predicted like output, but that kind of is limited because there are false positive cases. So to overcome that, a lot of works recently started to employ language models itself as a judge. So the way how it works is you give the predicted output from one model and then give it to a more powerful model, for example, GPT-4, and then you would prompt GPT-4 to give a score between a certain range. So that's one way of doing it. And another application is reward modeling. So a lot of people might be familiar with the term reward model from the RLHF pipeline. And if you think about it, actually, what the reward model is doing is actually evaluating the text from the policy model. So you're seeing how good the prediction is, and you're giving back signals for the policy model to improve. And last but not least, we have data quality filter. So there are a lot of like exciting recent works on this field. So basically the idea is that if you have a very good evaluation model, you could judge different, like if you have tons of instruction data, you can sort out the high quality ones and then use those labels to apply on enhancing language models by using SFT or DPO. Among these, I'll be particularly talking about LLM as a judge and reward modeling today. So why is evaluation hard? So if you think about it, as humans, we can actually like naturally discern the most important factors of assessment. This includes like criteria like brevity, creativity, tone, and cultural sensitivities. So based on the flexibility that human evaluators have, for a long time, NLP papers included human evaluations as part of their experiments. So in the figure on the left, you could see that InstructGPT used human evaluations to check what is the best learning rate and how the model improves if you scale up size. And GPT-3 paper also did this, along with the very famous like HHRLHF paper from Anthropic. So they were actually one of the first papers to ask whether a response is helpful or harmless. And here's a quote from one of my favorite papers, the top P decoding paper back from iClear 2020. So what it says is, while the metrics in previous sections gave us vital insights into different decoding methods we compare, human evaluation is still required to get a full measure of the quality of the generated text. So this states that human evaluation has been a very important method to assess the quality of text. But this is not to say that human evaluators are actually perfect, because humans are also very brittle to biases. So some representative examples are the central tendency bias, where, for example, if you ask a human to give a score between 1 and 5, they tend to give 3 a lot instead of 1 and 5. And also there's a very famous bias called the length bias, where people prefer longer outputs, regardless of the quality. So there was a result from the Flask paper from KAIST showing that if you use different criteria to evaluate by human evaluators, the interhuman agreement tends to vary a lot. So for relatively intuitive criteria like correctness, humans show very high agreement against each other. But for subjective values like readability, they show very low interhuman agreement. And there were similar results from the human feedback is not gold standard paper. So also one important thing to note is that human evaluation actually takes a very long time, is very expensive, and is oftentimes hard to replicate because you don't know who you're going to recruit if you conduct that evaluation. So one of the tables from Flask paper showed that when you compare model-based evaluations by using GPT-4 and with human-based evaluations, actually just prompting GPT-4 to judge the quality of text is much cheaper and much more faster. And Surge AI is very popular for like requiring lots of money to judge quality of text or getting annotations. So these kind of situations call for this question of whether can't we use AI models, which we believe becoming much more capable in the past years, to directly evaluate other AI models that we are developing. So I've been pursuing this direction, but if you think about it, also using language models or other AI models as a judge also have a lot of challenges. So first of all, LLMs can't naturally discern the most important factors of assessment. So a lot of evaluation papers ask GPT-4 to grade based on the helpfulness or harmlessness of the response. And compared to what we do with human evaluation, that's very not flexible because we don't consider the more fine-grained aspects that I discussed previously. And also, LLMs are also brittle to biases. They also have the length bias. And there's another type of bias called the self-enhancement bias, where AI models tend to prefer their own outputs. And I think this is the most important part, where there's the problem of reliability. So if you're asking AI models to make problems with data augmentation and solve the problems, and then ask AI models to grade them, there's no human intervention. So humans are kind of out of the loop. So that kind of leads to this problem of reliability, of whether we could really rely or trust the judgments made from AI models. So there are a lot of challenges, but particularly with the Prometheus model series, one of the problems that I've been interested in was this problem of, I think that the biggest problem currently is that we often do not specify how we want our LLMs to be evaluated. So if you think about it, actually determining what a good response is very ambiguous in nature. So we wanted to resolve this. Yeah, so I'll be talking about how we try to tackle that in our Prometheus model series. So there's 3 papers. The first paper was Prometheus, inducing fine-grained evaluation capability and language models. And then we had another paper called Prometheus-Vision, where we tried to expand that into VLM space. So it's a paper of VLMs evaluating other VLMs. And then recently we had a follow-up paper of the Prometheus model called Prometheus-2, where we try to improve the performances. So while working on the Prometheus papers, there were 3 main considerations. I'll go one by one. First thing is we wanted the open source evaluator LLM. So there might be lots of reasons why we might want this. The first thing is that, especially for evaluation, if you think about it, we want to be very fair, but actually relying on closed source models kind of contradicts the nature of evaluation because you don't know what's going internally inside the models, closed source models. And that kind of hinders understanding why a certain judgment might have been made. Also, there's the issue of controllability where as proprietary models, we can't control the version updates and they tend to give different results. And also, we don't want to send our private data to companies while conducting evaluations. And last off, we have the issue of affordability. I don't think this might be a big issue for big tech companies, but as a person from academia, actually, it's really quite not happy to having to pay OpenAI money just to evaluate my model. So I wanted to have internal evaluation pipeline. And the reason why we challenged this problem is actually we believe that evaluation might be easier than generating or solving the problem itself. So we believe that based on this, a weaker LM, if it could obtain evaluation capabilities, could function as an evaluator to judge stronger LMs as well. And second off, we wanted to have an open source evaluator LM that possesses good evaluation capabilities. So actually, this is very vague because it's really hard to define what good evaluation capability means in the first place. So we try to measure this in 2 ways. First is achieving high score correlations with potentially strong evaluators. So what I mean by strong evaluators is what a lot of people would agree that would possess good evaluation capabilities. So that would include humans and proprietary LLMs. So we're assuming that they're the gold standard and trying to measure the correlation. So indeed, in the Prometheus 2 papers, we observed this, where GPT-4 and Cloud 3, although they tend to vary a little bit, show very strong correlation between each other compared to that of the weaker LLMs, weaker evaluator LLMs, like GPT Turbo 3.5 Turbo, Llama 2 70B, or the Prometheus 1 model. And the second kind of method would be asking strong evaluators, like humans, to judge whether the assessment itself was reasonable. So this is kind of sketchy because you're asking to evaluate the evaluation results, but we indeed included this in the Prometheus 1 paper. And third off, this is the point I want to make most today. It's that we wanted the open source evaluator LLM to possess the ability to adhere on an arbitrary evaluation criteria, not only helpfulness and harmlessness. So the reason of this is because a lot of NLG benchmarks are mostly employing two coarse-grained axes, helpfulness and harmlessness. But actually, judging which response is more helpful or harmless can vary from person to person. And there are lots of ambiguities depending on the situation. So I brought a few examples. So first off, this is the overall evaluation pipeline. We give an input to the LM we want to evaluate and obtain the outputs. And optionally, we could provide a reference answer or another output to compare with. And then based on this, the evaluator LM would give a feedback and a score. And in fine-grained evaluation, what I'm going to talk about from now, adds just one more input component, which is the score rubric, which explains you should evaluate based on this. So here's one example. So for example, if the instruction was develop me a business strategy for creating a fintech startup strategy, you could just ask the LM to evaluate based on harmlessness, but a more instructive way to do this would be to check whether the response considers regulation and compliance requirements. So if I provide the instruction, the response to evaluate, the customized score rubric, and a reference answer, Prometheus would generate a feedback and a score. And this is also important when there are like contrasting evaluation criteria. So what I mean by this is, for example, if the instruction is asking what is the meaning and significance of containerization and explaining the role of Docker, actually these two responses do seem quite helpful if you just like look through the lens of helpfulness. But actually, if you ask in a more fine-grained manner, for example, whether the response accurately uses specific industry terminologies, meaning whether it's professional, the response B is better, although they were both helpful. In contrast, if you ask if which response uses more simple language for a beginner, actually response A is better. So you could see the point. And in Prometheus-Vision, we also tried to see if this could be applied in the VLM space. So there's only an addition of the image, and Prometheus would evaluate the text that was conditioned on this image. Oh, James, how much time do I have?
Let's see. You should have, at least like five more minutes.
Oh, I see. So to train these models, like basic idea was using synthetic data. So we generated all the data from GPT-4. I won't go into the details, but the main idea was handcrafting a set of score rubrics. We use them as the seed data and then expand them into many like evaluation criteria that we think might be important during evaluation. And then we would generate the instruction and the other components as well. So we use this data a lot. So the feedback collection is actually a direct assessment data, which is point-wise ranking. And the preference collection is a pairwise ranking data, which is for pairwise ranking. And also in the Prometheus 2 models, the novel idea here was merging models. So surprisingly, instead of just training a direct assessment model or a pairwise ranking evaluator model, the main idea was training both and then multiplying 0.5 and then merging the weights to obtain the strong evaluator line. So this surprisingly worked well compared to just jointly training the models, or actually jointly training one model on both formats, or a model only trained on one format. So I'll go over this in the later slides. So here are the overall results. You could see that, as I mentioned this figure before, Prometheus-2 indeed obtains high correlation with the other stronger evaluator LLMs, including Cloud 3 and GPT-4. And also this applies to humans as well. For pairwise ranking, we measured the accuracy to see if it could simulate human judgments on grading like responses. It showed the highest performance and was comparable to in-domain reward models as well. Here's some interesting oblations. So this is the experiment I mentioned before. So instead of training just one model on both formats, training separately and then merging the weights surprisingly worked well. So this was the main ingredient in Prometheus-2. And also, to see if this works well because of ensembling, we compared with training 2 direct assessment models with different random seeds and then merging them. And surprisingly, that didn't work very well. So this result shows that the effect of merging comes from unifying formats, not from ensembling. We tried to ablate the effect of merging the 2 models trained each on direct assessment and pairwise ranking. And this result kind of shows, so the green line is the results on the direct assessment formats, and the blue line is the result on the pairwise ranking results. So you could see that actually the optimal like performance is obtained when you mix 5 by 5 in direct assessment. And in contrast, for pairwise ranking, mixing with 3 by 7 is the optimal point. So this kind of indirectly shows that pairwise ranking helps direct assessment more than vice versa. I have 2 more ablation experiments from the previous papers. So one might ask, so what is enabling Prometheus to obtain better results or evaluation capabilities when you train on feedback data? So we compared the verbal feedback generated from GPT-4 and Prometheus. And in GPT-4, a lot of people said that the verbal feedback is too general or abstract. And in contrast with Prometheus, you could see that people see the error cases come from being overly optimistic or overly critical. So I think this is very interesting because it kind of tells you that if you train on feedback data, the resulting model obtains evaluation capabilities and tends to judge the response based on its like preference, because in some cases it would state that the response is too good than it should be, or it's worse than it should be. So this is kind of like inducing to judge the given response. And I also have a result from the Prometheus-Vision paper. And the overall like pipelines and results are very similar with the original paper. One interesting thing to note is that when you provided text-rich images, the evaluation results were not that good. So I think this is one of the limitations we have with VLMs. It's that we rely on the CLIN model, but the resolution is not good enough to distinguish very text-rich images. Here are some takeaways from these overall experiments. First of all, training on feedback data indeed enhances evaluation capabilities. And if you merge the weights trained on direct assessment and pairwise ranking, this enhances the performance on each setting. And training on feedback data leads the model to be critical instead of providing general verbal feedback. And last of all, the same recipe works exceptionally well for training VLM evaluators as well, although they do function poorly on text-rich images. So yeah, I think that's all I have for today. I'd be glad to take questions if there are any.
Awesome. Yeah. Thanks a lot for the presentation. For the great insight, and I think this takeaway slide is very very helpful for us to understanding all the the key things that that you presented. Okay, there's a question on the chat from Craig. I can read it out for you. Well, he has two questions. Number one is that are we not the place where I cannot even read it.
So actually, I think I
Yeah.
didn't understand the first question. Could you elaborate?
In what way would you like me to elaborate?
Yeah. So what do you mean by mechanical combination?
Oh, mechanical combination. This is studies that are back at the University of Chicago kind of a while ago. But basically in medical diagnosis and stock market picking, where if you had experts recognize what the cues were and then do a mechanical combination meaning an algebraic combination that the expert probably would not be able to do, then you would get a better result. But the expert didn't want to be evaluated for their ability to recognize cues. They wanted to be recognized for their ability to do a combination, but they weren't very good at doing combinations. They were good at recognizing cues. So in a way, what you're doing is similar to that or related to it, because you're finding that and that's the second question kind of leads into that. Is there a data set size? Is the data set big enough where the result gets better than cues recognized by experts, or is it always going to be the case that the data set is not as good?
I think we could start with the second question. So
Yeah.
this is asking for whether increasing the data size improve the evaluation capabilities.
Right.
Am I right? Yeah. We did a simple ablation on that. I didn't include it in the paper, but as you increase the number of data, the performances indeed did improve.
Sure.
For the first question, I think I totally didn't get due to lack of background. I think we could talk about this more later on.
Yeah. Just do a little, do some Google searches on mechanical combination. You'll find some stuff.
Yeah, maybe I'm too young to know all the background.
Okay. Maybe just one more question from my end is, I think the last 4 years you mentioned that like there's this limitation, right, when bringing this approach to vision language model. So I guess for future work, what do you think are some of the ways that the recipe can get improved for multimodal models, right? Not just image, but also like audio and video language model in the future.
So yeah, that's a great question. One thing that I'd like to add on before explaining that is that actually when you train evaluator LLMs or VLMs, the backbone model is very important because, for example, when you want to judge things like mass rationals, whether the rational to derive the final answer was correct, first off, you could do it in either ways. You could train to judge mass rationals, or you could have a backbone model that's very good at math, teach it evaluation, and then expect it to have a composition of bringing the evaluation capabilities and the math capabilities together to judge math rationals. And surprisingly, the second approach kind of worked well because if you use stronger backbone models, it seemed to generalize to other evaluation domains where the model didn't train to evaluate on. So why I mention this is because I think currently the VLM backbones, at least open source models we have a bottleneck on the vision encoder side, where it's not very good at distinguishing text-rich images. So I think one way to overcome this is to first off have a very good VLM backbone that could process text-rich images very well. And then if we apply the same recipe or add more evaluation data on evaluating text conditioned on text-rich images, I think it would improve.
Yeah, that makes sense. Yeah, just here we just need to build better base foundation models for for images, right? And from there we can the downstream evaluation will increase as a result of that.
Absolutely.
Yeah. Great. So I think that's a good segue into the second part of the webinar. Yeah, Nikhil, do you want to go ahead and share your screen and go with your presentation?
Do that. Let me know once you can see it. I also have audio, so at any point, if you can't hear any of the clips, just let me know. And
yeah. So when you share on Zoom, make sure that you check the box that you can share audio.
Great. Okay. Is that good?
Yep.
Is that great?
Yeah, I'm seeing it.
Okay, awesome. So yeah, really cool talk, Seungone. Thanks for that. I'm going to talk about multimodal models for enhanced audio processing and creation. I'll mention a few projects, but the interest in audio and creativity comes from, as James said, my background in music. I worked a fair bit in the industry, both as a producer, as a film composer, and as a sound designer. And that got me curious about this idea of developing precision tools for human AI co-creation, observing that largely our tools have been built on the backs of successful computational technologies like video editors and audio editors. And I'm very interested in how we can build next generation tools for that. So I work kind of across the stack, computational models, all the way to like studying how people can make best use of them to further their own ideas. And I've worked on this in a number of different ways, and the reason I mentioned this when James mentioned the Multimodal Weekly, I realized that most of these projects have a kind of focus on multimodality in some way or the other. And this isn't even all the multimodal projects, just all the ones I could get onto the screen. So multimodality is really at the core of this. For example, I did some work on trying to, for example, simulate room acoustics, model and simulate room acoustics from visual input. These room acoustics can be hard to capture and simulate in the real world, but in this we use a conditional generative modeling approach to try to tackle this with relatively sparse visual observations like photographs or even drawings. The idea being that given an input signal, could be speech like this. Let me know if you hear it.
There once was a young rat named Arthur who would never take the trouble to make up his mind.
So this is anechoic. There's no acoustic environment impact on this, really. But we can transform it to sound like it was recorded in a place like the International Space Station.
There once was a young rat named Arthur who would never take the trouble to make up his mind.
Which is a place you probably couldn't go and record, but using this sort of visual commonality with spaces in the real world and this conditional generative modeling approach, we can try to simulate this.
There once was a young rat named Arthur who would never take the trouble to make up his mind.
There are no reflective surfaces here, and so there's no reflections really in the audio. And I'll give you one more example where it's like a cave, and this is an animated cave, so it's not a place you could even realistically go to. It's not a photograph.
There once was a young rat named Arthur who would never take the trouble to make up his mind.
So this is a kind of multimodal problem where being able to do the simulation from easily obtainable visual observations like photographs or renderings can be really useful for simulating their acoustics in different applications like film, television, music, video conferencing, and potentially even others. Another project I thought I'd briefly mention, since there's a focus on video, 12 Labs, is work that I did while interning at Netflix on learning counterfactual cross-modal pairs for audiovisual representation learning. The core idea here is to try to encode the invariances that we expect from representations of creative media like film, thinking about scenes that look similar but sound different largely due to fairly arbitrary differences in the speech content of different scenes and that don't change the semantics of the scene. For example, you might hear voices like that in a crowded restaurant, and then there might be a couple speaking like this, and what they say might change from scene to scene, but the semantics of the scene are largely consistent. So maybe some of you have seen these clips of Meryl Streep's improvised takes from the movie Don't Look Up. These are different takes in which she's improvising what she says, but the scene semantics are the same. And as a human viewer, you can recognize the commonalities between these different scenes, despite the variation in the speech. And we call these instances counterfactual pairs. They don't really occur very often in the kinds of training data that we have. So what we do in this work is leverage a different signal, which are second language dubs of movies. These also have different sounding speech with shared semantics of the scene. So for example...
No, I get it. You got a lot going on, it's a lot of pressure.
That's an English version of this, and I'll play just 3 more.
No, ho capito. Hai tante cose da fare, sei sotto pressione. わかるよ。忙しいだろうし、焦りもある。No, entiendo. Tienes otras cosas, es mucha presión.
So across these different language versions, which you can see the variation in, there are common elements like the dripping drink, the background music, and even the characteristics of the speaker, the kind of voice, the emotional expression of the voice. And if we can learn the commonalities between these different scenes, we show in this paper that we have some pretty strong representations for different kinds of audio and video processing tasks that can come out of it. So watch out for this at CVPR this year. But mostly for this talk, I wanted to focus on a more creative work-oriented project directly called CTAG, which focuses primarily on audio in the context of sound design. This is joint work with my colleagues, Manuel Cherep and Jessica Shand, recently accepted to ICML. And this paper, we focus on creating sound, often for visual media like film and television, where you're doing sound design. So if, say you're working on a project and you think of a sound, for example, the sound of a bird tweeting, something that's amazing that we can do now is you can type this in as a text prompt and pass it into a model and get a sound like this. Or like this. So as amazing as it is that we can do this, these sounds are also noisy, they're prone to these artifacts, they have some limitations, and they're not like these crisp, clean, creative renderings of these ideas that you might have. So in contrast, when you think of that sound designers often emphasize abstraction. So, for example, the legendary composer and sound designer Suzanne Chani says bubbles don't make sound, but the magic of sound design is creating the concept of the sound and making it seem real. Suzanne famously used this to great effect in the 70s by creating a sound for a commercial for Coca-Cola, where it was completely synthesized using electronics, and that allowed them to go far beyond the limitations of what you could do by recording an actual opening a Coke can. So here's what it sounds like for reference.
Coca-Cola pop and pour.
Can sort of evoke that refreshing experience more than a realistic version could. I'll let you hear this a little bit from award-winning sound designer Mark Mangini from Dune and many other things.
How did Pablo Picasso find a way to make a portrait out of squares and circles? Those abstract impressionists found ways to create art with objects that weren't what they were trying to express, but found a way to mold them to do just that. Sound designers, we think in abstract ways, and our brains have been trained over the years to find abstractions of what we want and create associations. This is how our sound designer brains think.
So you've heard a little bit about it from the context of advertising and film. It's also central in music. And one of the tools that came from music that sound designers use in a variety of different contexts is called a modular synthesizer. You can think of these as graphs of signal generating and processing components that you can plug into each other and tweak in really precise ways to enable generating a wide variety of different sounds. So I'll let you hear just a little bit about it from 2 legendary musicians, Herbie Hancock and Quincy Jones, talking about this in the 80s.
It's interesting because, these instruments were designed for people to use, Right. It's just a tool, another tool. The way an axe is a tool, an axe can be a tool to cut wood to build a house, or it can be a tool to slaughter your neighbor, The same thing, a synthesizer can be a tool to really hurt people's ears or interfere with their lives, or it can be a tool to make a really nice sounding instrument that can really affect people in a positive way. And it all depends on the person that's using them. People blame machines very often for the machine's fault. How can it be the machine's fault? We have to plug it in. The machine doesn't do anything but sit there until we plug it in. It doesn't plug itself in. It doesn't program itself yet.
It's on the way, though.
It's on the way.
So 40 years later, that self-programming synthesizer is finally here. And that's what we do in this work, CTAG. To generate sounds, what we do is take your prompt, and rather than try to render it using a neural network directly, which as we saw is artifact prone and has other issues, we try to abstract away the sound by programming a synthesizer to recreate some of the semantics of the sound. So for example, with bird tweeting, we get sounds that sound more like this. We can also do things like interpolate between sounds. Like we can go from bird to chainsaw to helicopter, for instance. The core idea behind CTAG and the synthesizer, accelerated sound synthesizer we built that it depends on, is that you get the benefits of a modular synthesizer in the sense that these sounds are tweakable using interpretable parameters that you can actually play. They also have the benefits of modern generative models in the sense that you can guide them with text descriptions. They produce these really high quality sounds, and the process of tweaking the sounds is very, very fast. I played these sounds earlier from Audio LLM and Audio Gen. And as amazing as those are, they have these kind of limitations in the bandwidth, for example, of the audio signal. They have these background noise that you may or may not want. And by contrast, because we use a synthesizer, we don't actually have that, and we only have background noise if it's actively generated. Another benefit of this approach is that rather than large parameter sets and latent control spaces, CTAG exposes only 78 parameters. That's all the entire system contains for synthesizing the sounds. And these are all things that you can causally interpret. They're actually knobs that come from modular synthesis. So the sort of classic human approach to doing this sort of process is to listen to what a synthesizer gives you and tweak until you get what you're looking for, which might change, but that's sort of the basic setup. And what we do is formulate the same idea as an optimization problem where we try to maximize the similarity as a function of the parameters of the synthesizers between the text description that you have and the sound that's coming out of the synthesizer. And if you try to do this naively using a gradient-based optimizer, it doesn't work incredibly well because, of course, modular synthesizers weren't designed to be smoothly differentiable, and even random search can work better than that. And I won't go into all the details, but the core idea is we use a learned evolutionary strategy to do this, which ends up giving us much, much better results. I'm going to skip over some of these in the interest of time. There are a lot of ablations and sensitivity analyses in the paper where we try different synthesis architectures, durations, and strategies to optimize these. I'll play a few examples for you of different kinds of sounds that we can generate this way. And then the ability to create these stable and interpretable interpolations, for example, between spin machine, you can listen to how the individual features of the sound change. Here's another example from train horn to chainsaw, where you can actually hear how the pitch descends as it tries to interpolate between these two sounds. All right, one more. Train wagon to engine revving, and here you can actually visually see this change. You see how the sound gets longer and the kind of variation comes in. I'm gonna just skip over this briefly to say that we did a lot of evaluation of how these sounds qualitatively differ from the existing sort of generative model sounds. And there are a number of features on which these sounds are markedly different. For example, high frequency content and the degree to which it's compressible using standard audio codecs, which suggests a sort of perceptual simplicity or redundancy in the data. And then we conducted a user study where we actually tried to see how people hear these sounds. And we found that people can actually pretty accurately recognize these sounds on par with something like AudioGen, which is a really strong baseline. but they're less confident about what these sounds are. And we call this the abstraction gap, the fact that they are recognizable, but with less confidence about what they are. Another thing we notice is that people consistently rank these as higher artistic interpretation than sort of existing generative models. And the identifiability, of course, varies by prompt. Some prompts have a very low baseline identifiability, for example, like truck air brake, which we often don't even know what that sounds like in the real world. Cool. So that's creative text audio generation via synthesizer programming. It's open source. You're welcome to try it. Would love to hear your feedback if you do get the chance to. While I want to very quickly just touch on a project that we just recently did building on this called Contrastive Learning from Synthetic Audio Doppelgangers. And I mentioned contrastive learning earlier in this sort of counterfactual, looking similar, sounding different project. In large part, contrastive learning relies on what are called data augmentations, which you can see on the left here, like spec augment, which masks audio spectrograms, or effects chains, which can apply these effects to audio to try to make them sound a little bit different and learn the similarity between them, learn what stays the same. As powerful as these are and useful as they have been shown to be, they operate at the level of the observed data, not the underlying data generating process, as you would observe in the real world when you hear different kinds of sounds that come from the same source. So they really are like statistically altering this data without actually manipulating the causal mechanisms that produced it. And this results in really high correlation between these samples. And also limited control and interpretability. So what we do in this work is we take the synthesis approach because we see that like the synthesizer can recover real world concept distributions, like realistic sounds. And we try to synthesize random sounds that we can slightly perturb to make different versions of the same sound. And we can control the degree to which we perturb it, as you can see in this graph here with delta. And even with delta equals 0.25, you can see that there are some similarities. So at 0.5, there's almost nothing in common between these. But in the middle, you can see these sort of like wedge-like patterns at the beginning and these bands that occur throughout the sound. We call these audio doppelgangers because they have this kind of subtle resemblance. The first thing we showed is that we can generate the sort of controllable diversity between positive pairs in a contrastive learning setup using the synthetic approach. And in addition to just being able to do this, something that you can't do with augmentations, we can also do like fast on-the-fly data generations. So we don't have to store anything on disk. This all happens in memory on a single process, batched. So you don't need a lot of CPU horsepower to do this. This can all happen very fast on the GPU in one process. We only have one hyperparameter, which is quite interpretable. It's just the amount of perturbation. And you can sample from different synthesizer architectures, considering that it's this graph of components to generate widely different data distributions. So high-level result, we started with like a random ResNet 18, random initialized weights with a linear probe tuned at the end for these different tasks. And it performs pretty well on some of these tasks. Then we introduced training on a VGG sound, which is a large video data set. We used only the audio portion here with some effects chain augmentations. And of course, we outperform in most cases the random weights, except for Vive. One task, for some reason, doesn't seem to impact it much. But overall, we're getting better results with real data, as would be expected. Then we try an approach called temporal jitter, where you sample different time slices from the same audio clip, and you treat those as positive pairs. And that gets even better results. We throw in our synthetic data. This is like no delta, no controlled variation, just one synthetic sound with some augmentations applied to it. And we see we're actually competitive on some of these tasks. We're not doing too bad. So the synthetic data distribution is enabling us to learn something that's useful for real world sounds. And then when we throw in our best results from actually using this delta to create variation between these synthetic sounds, we're actually the strongest performer on 6 out of 8 of these tasks, beating training on this real data, and at the very least being very competitive with it. Of course, there's a large search space of augmentations, and we're not saying that synthetic data is always going to be better. It's more like we can get really good results on these tasks using just synthetic data, even with a relatively simple backbone, all without ever seeing a single real sound during training time. And in a way that's much more efficient. So yeah, it's my talk on multimodal models for enhanced audio processing and creation. And yeah, if you're interested in any of these things, you want to talk about them, I know we have limited time here, but you're welcome to reach out over email as well.
Yeah, awesome. Thanks, Nikhil. I think it is extremely interactive presentation with a lot of qualitative results, and yeah, super excited to I guess like be able to like hear and comprehend, right, the differences from your model. Yeah, I think excited to see the contrastive learning work on audio Doppelganger to be published in conferences soon. Yeah, is there any question from the audience related to Nikhil presentation and overall reactions? Maybe one question from my end is, I guess like I think you mentioned like in the CTAP model is only 78 like parameters controllable, elements, and a lot of those are actually very specific to audio, right? Like you're correct, and so I assume like your domain expertise of like working with audio for a long time help you like do this feature engineering, right? Work of like come up with these features and use them as input to the model.
So yeah, in this case, it's true that we designed some alternate architectures where we were relying on like existing paradigms in audio synthesis. So in those ablations that I kind of glossed over, we have some architectures that use more or fewer parameters and try to encode some biases that come from like historical audio synthesis tools. In the main architecture that we ran things on, the architecture itself is derived from like literature, so it's something we didn't actually come up with. And the configuration of which components land where are kind of given to us by prior work. So that's a case where the expertise is maybe not even so necessary, but it's true that like in general, trying to design these architectures, you do need some like kind of understanding of what the components are doing and what can be plugged into what and what's likely to be fruitful. We are something that I think would be really interesting and powerful is like to be able to design those architectures automatically. It's a hard problem because it's like non-parametric. You can have like arbitrary number of components configured in an arbitrary pattern. And there are some constraints in terms of what you can connect to what. So you have to like somehow obey those constraints, but also it's like a virtually infinite search space beyond that. And 78 parameters is very small. You could easily scale to thousands and still keep the process tractable potentially. So yeah, it's an open question about like how to design those optimally for the kind of real world sound design tasks.
Yeah. Well, maybe since this is like text to audio generation task, just as curious, have you considered like diffusion architectures or even like autoencoders, those kind of approach, and whether they like compatible with the task here or not, and the limitation as well?
Yeah, for sure. Yeah, we've been interested on kind of both sides, both the input side and the output side, in like bridging with sort of like generative models. So you could imagine like generative models that help you control the input better. So rather than having to do this like test time optimization, being able to like control the parameter space directly from some text prompts or even like simplified controls. So we're interested in that, and we've been working on some projects related to that. And then the other side, being able to transform of course, we're working with these synthetic outputs and they sound synthetic. And that's part of the charm, they come from this like long line of sound synthesis, but often you might want some realistic sounds, but with the interpretability and the control that the synthesizer gives you. So we're also interested in how you can do like that distribution transfer from the synthetic sounds to like the realistic sounds. And that could depend on something like a diffusion model. It's a challenging thing to train that end to end because of the unstable gradients from the synthesizer, but it's something we're interested in for sure.
Awesome. Yeah. Maybe one final question from my end is, this is more like the future of the field. You pretty deep into like academic research on specifically for audio enhanced processing creation, and I guess like outside of the academic context, in the industry, I think we also start seeing a lot of companies or like projects that are doing this stuff, right? Everything ranging from like 11 Labs to Suno to Udio, right? And even with the GPTO voice as well. Curious, like given like your domain expertise in the field, like how do you see this new software that bring you know, voice synthesis, audio synthesis, music creation to the mass, and yeah, how it's going to evolve over the next few years.
Yeah, that's a good question. You know, I'm always excited when the people are talking about audio and the news is about audio, because always feels like audio is kind of the underdog field in some ways, compared to vision and language. But of course, it's part of vision because it's part of video, it's part of language because it's part of speech. So I think it's exciting that people are paying attention to audio and thinking about it, both musically and speech and general sort of auditory perceptual capabilities. So I think it's very exciting that industry is working on these problems and trying to build like more general auditory perception systems that can interact end to end and don't like use text as a bottleneck or something like that. So it's very cool that we're doing that, and I think we'll see some really cool capabilities emerge from that. I think, you know, as I mentioned, like part of my interest has been like impact on the creative industries, and I think like, you know, we don't know exactly what's going to happen there. There's certainly challenges with like copyright and sort of like constraints that we need to be mindful of in terms of like how it interacts with the communities that already exist. So yeah, I think there's just some non-trivial challenges there in terms of like making it really fruitful for people to use. But yeah, on a technical level, I'm really excited about the things that are happening in industry, and I think you know, we all kind of work at different scales. Of course, in academia, we have to work at a different scale in many cases. But I think if we can like find the middle ground where like we can propose some ideas that enable new capabilities, like for example, one of the reasons we were excited about the synthesizer is like that it enables this new capability of like really precise control, and that precise control is really important for getting really precise outputs, which is kind of like the backbone of the creative industries. So we can find those like new capabilities and bring them to the more end-to-end approaches, bring them to like other domains. I think that's also really useful.
Yeah. Awesome. Yeah, thanks for pitching the vision, and you know, super excited to see some of your upcoming work and overall like how audio synthesis, audio creation, audio processing will improve with the more competitive you know, multimodals that allows them to be more performance while maintaining, you know, quality. So I think with that, we well roughly 3 minutes over time. So yeah, I wanna thanks the speakers for you know, the great presentation, and thanks to attendees for attending today. Yeah, the recording of this session will be available on YouTube probably within 2 or 3 weeks or so, and be sure to yeah, notify the speakers when they become live. Yeah, appreciate you spending your time on Friday with us, and you know, hope you all have a great rest of your weekend. Cheers.
Thanks all.
Bye-bye.
Oh,